Okay, so in previous class we learned about transformer. Okay, so we have learned some semantic segmentation network and also the object detection pipeline. Okay, and I will in this class I want to add a few more techniques regarding the training, and I think this lecture will be especially helpful for doing some of the assignment and some of your final project. Okay. And this is the review for what we have learned. So, I mean, this is the deep architecture that produce some output from the input. Okay. And this is, I mean, some method that can calculate our loss function. That loss is the distance between ground truth and our prediction. Okay, and we can interpret the calculation of the loss as also as the layer, because it is also differentiable layers, a differentiable module. So we can interpret as the layer. And I mean, the final objective, what we want is actually getting the parameter sector for this deep architecture to produce a proper output Y given any arbitrary image I, okay? And we want to make it similar to the ground truth Y. Okay. And actually, the distance between YGT and Y is defined as loss. So our objective is minimizing this loss. Okay. So our goal is we want to find the parameters of this sector for deep architectures to minimize the overall loss. Okay. And we are doing that by iteratively calculating this. Okay, this is called as the gradient descent algorithm. And to do that, using this deep architecture, we have to define these three rules for individual layers. If individual layers, for the individual layers, if we can calculate these three rules, then the entire deep architecture become to have these three rules. And we can actually calculate this D and D sector for every layers inside the deep architecture. And we can actually update the parameter sector. Okay, so that's what we have done. And also sector for the CNN is mostly the convolutional filter coefficients. They are the parameters we have to learn. Okay, and also of course the first layers are composed of convolutional layer, and later it is composed of the fully connected layer. So the weight and bias for fully connected layers, they are also the parameter sector, okay, in CNN. And in transformer, you may remember that there are three weight vector that can transform the image, the input sequence, input data to some of key quality values. This is Q. So this is the weight. This is actually the important parameter we have to learn during the transformer training. And also there are FFN network, which is the actually MLP layer having this kind of weight and bias. And this is another parameters we have to learn. Okay. So anyways, deep architectures are having their parameter, and using this gradient descent rule, we can iteratively update that using the data. And also, you have to remember that PyTorch makes this part very easy to implement. So without PyTorch, we have to implement this backward rule and parameter update rule by ourselves. But thanks to the PyTorch, we don't have to implement those, gradient calculation part by ourselves, except that PyTorch is providing easy interface to calculate the gradient automatically using some approximation algorithm. So regardless of the forward rule, it can automatically calculate the gradient. So we don't have to care about how to calculate gradient. So, and also the function we can call for calculating the L dissector is this function. And optimizer, if you call optimizer.step, then this calculation is once done. Okay, so parameters are once updated. And also you can omit the parameter update rule for some of the layers inside the deep architecture if they don't have any parameters. So yeah, this is the example for the CNN. So any differentiable, but I mean, except for the CNN, any differentiable layers can come here between the input and output. But so far, CNN before transformer, CNN was the best architecture that can map RGB image to the semantic labels. So researchers have used that. But nowadays, transformer, they are replacing the CNNs in many image domains. And this is the code that you already learned. Okay, so this is the model definition part, and this is the training code. Okay, so you can use the same code for training any arbitrary deep architectures. And this is the gradient descent. Okay, and actually this code that you already seen implementing this kind of gradient descent concept. Okay, I will skip this part. And actually, this is gradient descent, and this is the implementation for the stochastic gradient descent. The difference between SGD and GD, I already explained that. So SGD, it uses the small batch to update the parameters for those small batches, but GD updates the parameters after seeing all the data. Okay, so the only difference is you have another loop for seeing loading the small batches and update your parameters for that small batches. That's happening in the SGD. But I mean, in the aspect of the training data, gradient descent is more optimal, but what you are aiming to is getting good accuracy in testing data rather than the training data. So getting the best model that fit to training data is not desirable always. So, I mean, SGD, it is suboptimal for the training data, but in practice, it works better than GD for the testing data. So we are using SGD. And also SGD is more efficient, I mean, to implement if the data is big. So SGD is more practical. Okay. So this is, for this, I already explained that, so I will skip it here. And AlexNet, as I told you, that was the first successful deep architecture that appeared in the year of 2012. Okay, and they have, I mean, 4 innovative points in their paper published in Leaves. They have 4 innovative points. But today I will, I mean, these points I already explained to you in previous lecture, but today I will, I mean, re-explain the first part again. I mean, the success, one of the most, I mean, important factor for success of the AlexNet might be they first use the multi-GPUs for training the large scale data. So, I mean, that's one of the very important successful point for the AlexNet. And also, they use large scale data with data augmentation. So today I will explain you how what is this data augmentation. And Sanely, I already also explained this ReLU part. So there are several nonlinear layers in the deep architecture. For example, tangent hyperbolic and sigmoid, okay, and ReLU. But the reason why ReLU performs better than other nonlinear functions in practice is this kind of function, they have if the input values are too large, then their gradients are becoming simply to converging to zero due to precision issue. So if their input is too large or too small, so because of that, this kind of nonlinear functions are not very practical. Okay, sometimes it hinders the stable training, but ReLU, in practice, it is helpful for faster convergence. Okay, so people and also ReLU is first proposed in this RLXNet. Okay. And dropout, this is also a very important aspect. Okay, so today I will explain a few more insights about these two components, dropout and data augmentation. And AlexNet, you already know the code for this. And so today I may have to explain to you about this overfitting phenomenon. So overfitting means the model is overly fitted to the training data. So when model is overly fitted to the training data, we call that as overfitting phenomenon. But I mean, it is similar to the difference between SGD and GD things. Okay, so here I explained that GD is more optimal for the training data, but our objective is getting good accuracy for the new testing data. So sometimes, I mean, because of that, because of this discrepancy, GD is not that optimal for our objective. SGD, that is not optimal for the training data, but in practice, it can give us better model than GD because we are, our aim is to get the model that performs good on the testing data. So when a model is overly fitted to the training data, then there are high probability that the model does not work well for the testing data. So, I mean, even though the training, the model is working good for the training data, I mean, it sometimes doesn't work well for the testing data. Okay, so we have to actually reduce that kind of phenomenon. Okay, so this is anyways the overfitting phenomenon. So and actually there are multiple ways to reduce this overfitting phenomenon. Okay, but one of the most popular way to reduce this overfitting is having another data called as validation data. Okay, so during the training, we use the training data, and during the testing, to evaluate the model, we use the testing data. Okay, but during the training, we can have we can also further divide the training data into, for example, 90% of the original training data and use the 10% of the original training data as the validation data. We can further training the low training data into these two types of data and can have extra data for validation during the training. So this is the graph for accuracy or error according to each epoch. Epoch means after we see one entire data, then we call that as one epoch. So normally the training error and also the testing error both reduce as the epochs go. Okay. So training error means uh, if we train the model using the training data, then the model's parameters get fitted to the training data, and we evaluate our model on the training data we trained. Okay. Of course, their error becomes less as the epochs go. And also for each model at each epoch, we can evaluate their testing performance, okay, by learning on the testing data, and we can calculate the error, okay, for their result. And also we can evaluate the model using validation data set as well. Okay, so for example, let's say this is also the denoting the validation error. Validation error means the error calculated on the validation data. Okay. Of course, it will be reduced. Okay, and both validation data and testing data they are not seen during the training. We only training our model using our training data. Okay. So validation data set, that is also unseen data. But when evaluating testing data, we can actually measure their, accuracy at every epoch. But for the benchmarking, we can do that. But if we do that, if we see the testing, accuracy to choose the model, it is regarded as cheating. Okay, so let's say if error goes down, and let's say if the error goes up again, we cannot choose this model by seeing the testing accuracy. That is regarded as cheating. So during training, we are assumed not to use this testing data. And when choosing the model, we will evaluate the model using the testing data. Okay, so during the training, anyways, we are prohibited to use the testing data. So we actually have additional validation data to measure their accuracy. And this validation data and testing data, their tendency might be same because both are randomly chosen data. During the training, testing, validation data splitting, we use the randomness. So we are assuming that the characteristic of validation and testing, they are roughly same. So if testing data, their accuracy have this kind of tendency, then validation data, they will also have similar pattern. Okay. So without seeing the testing accuracy, by seeing the validation accuracy, we can see testing accuracy also might be going up at some epoch, after some epochs. Okay. So we can actually stopping the training at this point when the accuracy, validation accuracy goes up, error goes up, we will stop the training at that time, at that epoch. Okay? Even though the training accuracy goes down, we have to stop there because our aim is not having the model during the training, but having the good model for the testing or unseen new data. So we have to stop the training at this point. Okay? So these kind of techniques are called as early stopping. So we can train for 1,000 epochs, okay, without having validation data. But if we have this kind of additional validation split, we can see their accuracy before the maximum iteration and can stop the training early. So that is called as the early stopping. Okay. So this early stopping, having the additional validation data and performing the early stopping, that is one way to reduce the overfitting. Okay. So this is a very interesting figure that I want to share with you. I mean, describing the overfitting phenomenon. So, I mean, when generating the model, let's say the model is roughly, I mean, in this example, it is exemplified with the bed. Okay, when making the bed, we have to, I mean, of course, we can see 3 to 4 men when making the bed. Okay, so measuring their height and width, we can design their width and height. Okay, when making the bed, but if we overly fit our bed to this 3 to 4 person, okay, or even one person's sleeping pattern, okay, I mean that bed is overfitted training person, okay, training data, okay, right? So if we make bed seeing just one person, okay, then that bed cannot be used to other persons in the world. Okay, so this kind of situation is called as overfitting phenomenon. So it overly fitted to the training data, so it cannot be generalized, usable for unseen new testing data. So that is the overfitting phenomenon. Okay, so because of this, I mean, we have to maybe have the additional person as the validation data to see his sleeping pattern is fit to this bed or not, okay? And check if the bed is useful or not, okay? Anyways, our model have to be this form and can be usable, I mean, generally for multiple purposes, okay? So that's a good bed. Actually, that's similar to having the good deep learning models, okay? And yeah, this is illustrating the overfitting phenomenon in feature space, okay? I mean, this is the, I mean, I already told you that in this 2D space, if we have the straight line, that is meaning the linear equation, which is the simplest form of the, I mean, equation. So maybe this is the linear equation. And I mean, and also if we have more multiple order for this X, then it becomes to have like this kind of complex curve, okay? So, I mean, but, so, I mean, linear to this kind of I mean, orders larger than 2, they are called as complex function. I mean, this is more simple to complex, okay? I mean, this is similar to, this is having a simple form, okay? Having some straight line boundaries, but this is having similar to having kind of complex curve, okay? So our model have to have less order. Okay, less order is desirable for the generalization ability. Okay, but I mean, our model's order have to be complex enough to represent the, I mean, proper boundaries between the data. Okay, so I mean, this is this kind of linear equation is sometimes very simple. So let's say if there are two classes, this is denoting first class and this is denoting the second class. So this X and O is denoting the data sample from different classes. And if we have only linear function to discriminate these X and O classes, then let's say in the left side of this straight line is X class and right side is O class. I mean, this function will operate it like that. Then many X samples will be wrongly classified. Okay, because the classification function itself is too simple, so we cannot correctly classify. I mean, the accuracy of our model is less. Okay, so in this situation is called as underfit situation, and overfit situation. You can interpret it like this. So our model's order is too complex. I mean, this is the actually training feature space. Okay, this is denoting the training feature space. Even for training data, this in the underfit situation, the error itself is quite high. We have a lot of wrongly classified samples, training samples in this situation. But in the overfit situation, for the training feature space, we can get 100% accuracy. Okay. However, for example, this part, I mean, kind of seen as ad hocs. Okay. We have to regard this kind of data as maybe there could be some error in the training data collection stage. So we somehow have to regard this kind of data as some error during the collection stage. So, and can have to ignore this kind of data. But in this overfitting phenomenon, the model is overly fitted to the training data. So it cannot avoid this kind of exceptional case. And the boundary itself could be like this. And this can cause the testing error, actually. So even though the real boundary is like this, because of this exceptional training data, the boundaries are obtained like this, okay, in the overfitting phenomenon, okay, in the overfitting situation. So in the normal fit situation, the most desirable situation is the normal fit situation. And in here, we have to have the model considering two things. We have to keep our model as simple as possible, okay? So we have to avoid too complex model, okay? So we have to keep the model simple as possible, but have to also avoid this kind of underfit situation, and also maximize the training accuracy. We have to do both things. Okay, underfit situation, our accuracy during training is not maximized. Okay, the model is simple, but it cannot represent the data properly. But in the normal fit situation, we can maximizing the training accuracy and keeping the model as simple as possible. Okay, that's the normal fit situation. So, anyways, we have to get the model as in this normal fit situation. Okay. And one, as I told you, this kind of early stopping technique, that is a proper way, one way to prevent the overfitting. And the other naive way to avoid the overfitting is increasing the size of the data. So, I mean, let's think about the situation where your model is overfit to world data, okay? So world data that I mentioned here is all the data we can get from this world. Okay, so if we can make our model to overfit to all the data we can see from this world, then overfitting, that is not bad thing, because if we can, I mean, this means our training data will be the data that we can get from this world. So in this situation, it will be same as the testing data. There would be no unseen data for the testing. So actually in this situation, the testing data might be same as the training data. So make the model that can overfit to the data that is same as the world scale data. That is the very good thing actually. But in the reality, we cannot achieve this because data, world scale data is too large. Okay, so we cannot achieve this actually. But we can actually increase the size of the data and secure the million scale data. Okay, securing the over million scale data, that is, have the similar, but not exactly similar, but anyways, uh, have some effect similar to have the world scale data maybe. So anyways, increasing the data size over this million scale data and make our model to overfit to those kind of million scale data is helpful for preventing the overfitting. Okay. So anyways, increasing the scale of the data, that is another way to reduce the overfitting phenomenon. Okay. Actually, there are many articles nowadays that training the model on very large scale data. Even they can provide to our model to have the generalization ability. Okay, so this is actually very good way to avoid the overfitting phenomenon. And also, the other skill that I want to share today is the dropout technique. I already told this you when explaining the AlexNet. Okay, so you already see this kind of code when seeing the AlexNet part. Okay, here there are dropout. Okay, so when you use this dropout, it means some of the output responses are randomly removed. Okay, they are randomly removed. So sometimes these parts are removed and these parts are removed, but with the probability of 0.5. Okay, with a probability of p, they are randomly removing the output responses. That's the dropout things. Okay. So anyways, having some randomness during the training, that's helpful for avoiding the training, avoiding the overfitting phenomenon during the training. So overfitting means it overly fitted to the training data. So on purpose, we give some randomness to our model. Okay. So this kind of operation, they will change our model randomly during the training. So it makes our model overly it makes our model avoid the overfitting to the training data during the training. Okay. So yeah. Anyways, this kind of randomness during the training is helpful for avoiding this kind of overfitting phenomenon. Okay. And also dropout, this part is also important. So during the training, some of the components are randomly dropped, but in the evaluation model, which is the inference or testing step, this kind of random removing is not happen. Okay, so this dropout only have this kind of random dropping during the training stage, and it just operate as multiplying one, just the same. I mean, just nothing during the testing phase. So anyways, this kind of randomness, if it happens during the testing, then it can spoil the accuracy of the model. But if this kind of randomness are involved during the training, the remaining part are better trained during the training. Okay, so that is the motivation of this kind of dropout component. And also you have to know about this data augmentation. Okay, so I already explained this part as well. So how to say, this is the maybe figure that can effectively explain the data augmentation. So maybe from the raw data, we can, crop some of the region and rescale it to make the input data for the CNN. Okay, but we can do this kind of flipping or some kind of the, regional cropping. Okay, so if you apply the flipping, even though you apply flipping on this image, these two images are same, almost same, and have the same class inside. So in the aspect of the image classification, the labels will not be changed even though we apply this kind of flipping, but it can make us, give us to secure two images, so the data itself are doubled. Okay, compared to the without augmentation situation, the data is doubled. And also, if we apply this kind of random cropping, some regional cropping, so we will crop the original image with this kind of windows, then we can secure this kind of five different, slightly different images. And also, if we further apply the flipping, then we can secure 10 times images. Okay, so this data augmentation is an easy way to actually increase the size of the data. Okay, so increasing the size of data, that is helpful for preventing the overfitting. Okay, and this kind of data augmentation that can provide us easy way to increase our data. Okay, so actually in the AlexNet, this dropout and data augmentation that was successfully used, and they are recorded as the state of the art in ImageNet challenge. Okay, so actually that's easy concept, right? We can make a lot of data by applying cropping and some of the, flipping, and also even we can change their contrast or image characteristics to augment the data. Okay. So this is the interesting, the result from previous literature. So this green, you are seeing multiple tasks in computer vision domain. So some of the classification tasks, okay. So using various data set, you can apply image classification algorithm, and you can train your model for this kind of dedicated tasks. So green is denoting, in each task, green is denoting the model that is, dedicatedly obtained for each task. Okay, that is showing the accuracy for best state-of-the-art model, and this pink graph is showing the CNN off the shelf. So it means if we use the free CNN architecture as the feature extractor and train maybe the last layer for achieving this kind of task, okay, then the accuracy is sometimes better than green or sometimes less than green, okay. But if you do that using the data augmentation, definitely it is better than without performing the data augmentation. So data augmentation, it is always helpful. So I recommend you to do this during your assignments and the final project. Okay. And specialized CNN, that is anyways the way to achieve propose the dedicated CNNs and doing the fine tuning, then mostly you can get the best accuracy using this. But without that, these deep architectures with the augmentation that can produce almost already good performance compared to the state of the art. Okay. So anyways, you can also refer this data augmentation code when doing the project. Okay. And this is another way to increase the data scales. So, I mean, this is one of the largest scale data set published in ECCB. And nowadays we are also, anyways, frequently using this MS COCO data set. This is proposed by Microsoft. And the COCO data set is their name. And there are many images within it, and they have this kind of annotations. Okay, so image classification label, this kind of person, sheep, dog label, and also the bounding box object detection label, and also the semantic segmentation labels. Okay, and they collect a lot of data, and also they label it using the crowdsourced platform called as Amazon Mechanical Turk. Okay. So they involve actually 8 AMT workers to collect the labels. Okay. So, I mean, this red dot is meaning the expert, their precision and recall. Okay. So this is the precision, this is the recall. So, I mean, definitely if you go this way, that is the best label. Okay. So one expert have good precision, but have relatively moderate recall. But this blue dot is meaning AMT worker, which is general person. Okay. This number is meaning one AMT worker is used. Okay, 2, 3, 4, 5, they are used to collect the label for this MS COCO dataset. I mean, if you use 8 workers, that's optimal actually in the aspect of the recall, even have higher recall than the expert. But their precision could be less, but in the aspect of the recall, if we use 8 AMT workers, then that's the best, okay? And if they use more worker than 8, then recall is similar, but precision goes less. So they say they used 8 workers, okay? Anyways, they use these AMT workers to collaborate to collect the labels. So you can actually increase your data size by collecting new data and label it by human effort like this, okay? So this is visualizing how they collect the MS COCO labels. So they first obtain the category level label from the AMT workers. So from the image, they first label which category, which objects are inside the image. So dog and bottle, okay? And then they enforce AMT workers to have the spotting format, this kind of spot format labels. So they want to first achieve rough localization of the semantic objects using this kind of spotting. And then they enforce those workers to even have this kind of fine-grained semantic segmentation labels. Okay, so this is the procedure. They have this kind of gradual procedure to secure the pixel level annotations. Okay. And this is the real data. Real data collection. Okay, if you want to increase the data scale, then you can collect the real data. Okay, and even you can use some of the graphics engines to make the data. So this is the illustration of the synthetic data generated by the graphics model. So you can see you can see this kind of images are not real. Okay, they are actually rendered using the graphics pipeline. So if you refer this paper, then you can see how they render this. And nowadays you have the how to say, the GPT or any other stable diffusion model to generate new images. Okay, and using those generated images, you can maybe using some techniques to label it. You can use those synthetic data as the training data. But one good way, I mean, good thing using the graphics engines is they are rendered from the 3D models. 3D models. So you already have the how to say, ground truth for segmentation or localization bounding box or even 3D meshes. So if you use the synthetic data, that is very easy to obtain the ground truth. That is one merit of this synthetic data. And also this is another paper that uses the maybe game engines to generate the semantic segmentation labels and their images. But the images are not that real. So if you train the deep learning models using this data, then sometimes if the test, because of the testing and training, their RGB difference, because the testing that would be the real image, and the training data that would have this kind of not non-realistic RGB image. So because of that, there would be some accuracy drop. But in general, synthetic data we can secure a lot of large-scale synthetic data. So in practice, this is anyways very helpful for training our model. Okay, and another thing is the transfer learning. So maybe you have to use this kind of technique when doing your assignments or the final project. So I'm explaining. Maybe today I will explain this by this. Okay. So this is the AlexNet, already pre-trained on the ImageNet. Okay, so there are 5 layers of the convolutional layers and 3 fully connected layers. And this is the input image, convolutional layers, pooling layers, convolution pooling, and applying FC layer. And at the end, they will predict 1,000 1,000 dimensional probability that denote the 1,000 class probability. Okay. That's the AlexNet pre-trained on the ImageNet. But if you want to use this, because this AlexNet architecture pre-trained on ImageNet that have a lot of pre-trained information, because it's the very large scale data called as ImageNet, it already have accumulate very informative information for classification task itself. So it can be transferred to other small scale data. Okay, those kind of accumulated knowledge can help achieve the image classification for small scale data. So that is actually called as the transfer learning. So you can reuse all the AlexNet, okay? Even you can initialize your network parameters using that of the AlexNet here. So anyways, their parameters are initialized with the pre-trained AlexNet, and also you will freeze most of the layers, okay? This means you will keep the weights of most of the layers as the AlexNets, pre-trained AlexNets, okay? But you will replace only the last layer, because I mean, the new data set, it can have different number of classes. In the ImageNet, there are 1,000 classes, but in your own data, you can have C class, okay? For example, 4 class maybe. So, but let's say you don't have much data to train this kind of deep architecture, okay? But if you don't have enough data, for example, million scale data, your deep learning architecture will be overfitted to your small scale data, okay? So to avoid this kind of thing, you have to do this kind of transfer learning. So the earlier layers, those are already pre-trained on the large scale data, and roughly it can have uh, useful information for the image classification task. Okay, and also I explained that the former part of the CNNs, they are ruled as the feature extractor, and the later part, they are ruled as the classifier. Okay, so feature extractor, that is already pre-trained by the ImageNet, okay, data, which is the largest scale data. So we can only train the last layers, okay? Or sometimes we also unfreeze the previous layers as well. So anyways, we freeze all other layers and unfreeze the last layer, or these kind of layers are reinitialized, okay? And we only train this last layer, okay? Then this last layer is relatively small in scale, so they can be trained using only the small scale training data, okay? So these kind of things are called as the transfer learning, okay? And we can achieve the deep learning model uh, working for our own data, which may have relatively small scale training data. Okay, that's the benefit of this transfer learning. Okay, so this is also I'm showing that the example of implementing the transfer learning. So the AlexNet, this might be the easiest way to load the pre-trained AlexNet. So unless without this kind of thing, you have to first train your AlexNet on the ImageNet, okay? But without that, PyTorch is providing the ImageNet pre-trained AlexNet, okay, using this kind of code, okay? So the thing you have to do is just specify, just add this package and access the AlexNet, and using this kind of pre-trained flag as true, okay? Then this net variable is having the AlexNet that is already pre-trained, okay? So if you print out the net, then you can see this kind of AlexNet structure that have the convolutional layers and the FC layers after that, okay? So as I told you, it has the 1,000 dimensional output as the last layer, because that is already pre-trained for image classification for the ImageNet data, okay? That has the 1,000 classes. So to achieve the transfer learning, we may have to reinitialize the last layer and have to train this part, okay? So and also freeze all other layers. Okay, so this is for doing the freezing for all the layers. So if you do this p dot requires on the background and set that as false, then that is specifying that layers will not be used during the training. So that their parameters are not updated during the training. And you will initialize the last layer here to have 10 class, okay, to produce the 10-dimensional output because maybe your data have the 10 classes, okay. You reinitialize the last layer and maybe train further using your own data, okay. That's the transfer learning. I think this might be useful for fulfilling your assignment. And also, if you want to save and load the model, you can use this kind of code. If you want to save the model in some file, you can specify the path of the file, and you can specify the model, okay, and then save. And you can also load the model, okay, and reuse it in the PyTorch code using this kind of 2 lines of code, okay. Okay, so this is yeah, things. And later part, I want to explain a bit more about the gradient descent method. You already know that this is the gradient descent, okay? But there are a few more techniques that can improve this gradient descent. And actually nowadays we are using Adam optimizer. You may heard about this already. When doing the deep learning training, you are now using Adam instead of the SGD. So Adam is having some good characteristic compared to the gradient descent, but basically they are based on the gradient descent. So I will explain you maybe after the midterm what kind of benefit it is having compared to the gradient descent, okay? Okay, so I will finish here today and let's see after the midterm, okay? Thank you.